In this recording, we would start looking at the transport layer, and we'll look at the services that it provides, as well as multiplexing and demultiplexing. So our goals are to understand the principles behind transport layer services. So we'll look at multiplexing and demultiplexing. Then we'll look at reliable data transfer from a very high level, flow control, and we would look at UDP and how it provides connectionless transport, and TCP and how it provides connection-oriented reliable transport. So, the transport layer provides for logical communication between application processes that are running on two different hosts. Now, transport protocols run in end systems, and on the sending side, they take data from the application layer, basically application layer messages. They break them into segments, pass these onto the network layer. On the receiving side, the transport layer reassembles segments into messages and passes these into the application layer. Now, on the internet today, we have more than one choice for a transport layer protocol. The two main choices are TCP and UDP. There are other choices out there, but they don't see much real deployment. So, the network layer allows for logical communication between hosts, while the transport layer allows for logical communication between processes. The transport layer will rely on the network layer and enhances the services that the network layer provides. So let's think of an analogy. Say you have 12 children in Anne's house, okay, and they're going to send the letters to their cousins, 12 kids in Bill's house. Bill and Anne and the children are all cousins. Okay, so the hosts are the houses, and the processes are the children in those houses. Now let's say, the application messages then are the letters that the children write to each other in each house and place in envelopes. So let's say Anne and Bill are in the different houses, will collect the letters from their siblings and send them through the postal system. So as far as their siblings are concerned, Anne and Bill are the siblings who will demultiplex to the in-house siblings, and the network layer protocol is the postal service. So on the internet, we can have reliable in-order delivery provided by TCP, and TCP will provide congestion control, which is basically a way of regulating many senders on the network so that they don't inject so much data on the network that the network collapses. Okay, and then flow control is where we're trying to prevent a sender from sending so much data that a receiver is overwhelmed. Okay, so it's providing some feedback so the sender doesn't overwhelm the receiver with data. And TCP also allows for connection setup. UDP allows for unreliable, unordered delivery of datagrams. And it's basically a no-frills extension of the services provided by IP. In neither of these protocols do you have neither TCP nor UDP do you find any delay guarantees or bandwidth guarantees. Now let's look at a little bit at demultiplexing and multiplexing. So let's say we have two client processes, okay, running on these machines over here and over there, and they're talking to two server processes on a server. So multiplexing at the sender basically means handling data from multiple sockets. You add a transport layer header, which we're basically going to use for demultiplexing. And demultiplexing at the receiver means using the header information to deliver the received segments to the correct socket. Now, how does demultiplexing work? Well, the host will receive IP datagrams, okay? And each datagram will have a source IP address, a destination IP address, and each datagram will carry one transport layer segment. And each segment will have a source port number and a destination port number. each of these port numbers are 16 bits long. And so a host will use the IP addresses and the port numbers to make sure the segment goes to the appropriate socket. Now, there are other header fields as well, but we would ignore those for now. Now, recall that when we talked about sockets for UDP, that the socket that we created had the host local port number. Right? So if we were creating sockets in Java, we would have done something like datagram socket, my socket 1 equals new datagram socket 12534. So when creating a datagram to send into a UDP socket, you have to specify a destination IP address and a destination port number. Now, when a host receives a UDP segment, it checks the destination port number in the segment, and then it directs the UDP segment to the socket with that port number. What this means is that IP datagrams that have the same destination port number but different source IP addresses and/or source port numbers will always go to the same socket at the destination. So here is an example. Okay, we have P3 and P4 are client processes. P1 is a server process, and so we create a datagram socket going to port 9157, and we create a datagram socket, with port number 5775, but our server process is running on port 6428. Okay, so by the way, the 9157 and the 5775, those are the source port numbers. So that goes in to that socket. Notice the source port number is 9157 6428 destination port, so it goes into that socket. And let's say the response will go 6428 and the destination is 9157. And for the other, what do you think would be the source port number from P4 to P1 and for the response from P1 to P4? I'll give you a hint. The source port number here is going to be 5775. So you can work out what the destination port number is, and above, those will simply be reversed. Okay. Now, with connection-oriented demultiplexing, a TCP socket is identified by a for tuple consisting of the source IP address, the source port number, the destination IP address, and the destination port number. And in demultiplexing, a receiver will use all four values to direct the segment to the appropriate socket. So a server host may be supporting many simultaneous TCP sockets, and each socket will be identified by its own for tuple. Now, web servers can have different sockets for each connecting client. And with non-persistent HTTP, you're going to have a different socket for each request. So let's look at this figure. Okay, so let's say P3 on this host is talking to P4 on the server, and then we have two processes on host C, P2 and P3, that are talking to P5 and P6. Okay, so the request will go, say, from source IP A, source port number 9157, and the destination IP is B, which is the server's IP address, and the destination port is 80, and the response naturally will come from source IP B and source port number 80, and the destination IP is going to be A, and the destination port number is 9157. So let's say the request from P3 will come from source IP C, source port number 9157, destination IP B, destination port number 80, and the request from P2 will come from source IP C, source port number 5775, and source port number destination IP is B, destination port number is 80. So what do we see here? We have three segments that are all going to IP address B, but guess what? They're demultiplexed to different sockets, which, if you might recall, is quite different from what we saw when we were doing UDP, where we had all of the segments going to the same port because they had the same destination port number, 6428. So because they all, yes, they're all going to port 80 and destination IP is B, but they're going to different ports, sockets, because they have different source IP and source port numbers. Okay, it's quite common to have servers run with threads. Okay, so you may have a separate thread to handle different connections. It's very common these days to see that with HTTP servers, say Apache. Well, even when you have a threaded server, you're still going to have multiple sockets, okay, to handle each of the different connections that will come in with different IPs and different port numbers, even if we're doing connection-oriented demultiplexing. Now, this ends this video. In the next video, I'm going to talk about connectionless transport using UDP. Thank you.